Hey everyone, welcome back to another video by Camroom 5. Today's video is going to be about a new concept known as ion polarization, and we will connect this new concept with the stability of group 2 compounds, especially their nitrates and sulfates. So let's begin what this ion polarization is. Before we begin understanding ion polarization, I want you to consider two ionic compounds. Let's say I want you to consider magnesium. Let's say I'll make it a little bigger. Magnesium sulfide. And I want you to consider strontium sulfide. So sulfide is the same in both cases. But let's suppose I am making strontium, which is much bigger compared to the magnesium cation. So let's make it like this. These are two ionic compounds. +2 -2, +2 -2. This one is our magnesium sulfide. This one is our strontium sulfide. Actually, there is attraction between these cations and anions, which is our electrostatic attraction. And if you remember from O levels, the electrostatic attraction is always between oppositely charged particles. Now, what is those oppositely charged particles exactly? It's basically the nucleus of cation attracting the electron cloud of the anion, and you can say the nucleus of the anion attracting the electron cloud of cation. So the nucleus of the cation is trying to attract the extra electron, or basically the electronic cloud of your anion. So let me write that down. It's between nucleus of one ion and electron cloud of the other. Electron cloud of the other ion. So magnesium nucleus, the nucleus of magnesium tries to pull the electron cloud of sulfide ion. Strontium ion does the same. Let me make this diagram a little bigger. Magnesium ion has a very small radius. So basically the nucleus is very close to the valence shell and it has short distance, so it can pull the electron cloud really well. But when I consider strontium, there's a big distance over here. You can see the distance between the nucleus and the valence shell is really huge. So strontium ion is not much able to pull the electron cloud well. Now, let's go back to the big picture. What actually happens over here is that magnesium ion pulls the electron cloud of sulfide ion well. But when I talk about the same capacity of strontium ion, it cannot pull the electron cloud of sulfide well. As a result, what happens is that in the case of magnesium sulfide, the electron cloud, I'm just writing E-, the electron cloud of sulfide ion is distorted because it has immense pull from the magnesium side. But in the case of strontium sulfide, it doesn't happen. So the electron cloud does not distort much. Now let me draw it and what it looks like. Remember, this was our magnesium and this was our strontium. Let me draw it better. This was our strontium. This was +2 magnesium, this was +2 strontium. The sulfide was immensely distorted because of the effect of magnesium ion. It looks like this. But in the case of strontium sulfide, it normally looks like this. See, it is still spherical in the case of strontium sulfide, but it has immense distortion because of the effect of magnesium cation on it. So the sulfide ion has gone distorted in the case of magnesium sulfide, but no distortion in the case of strontium sulfide. This distortion is known as ion polarization. So let's first write the definition of ion polarization. Ion polarization. Let's write it down. It is the distortion of the electron cloud of an ion under the pull or attraction of the cation. Ion polarization gives us two more definitions. One is known as polarizing power. One is the definition known as polarizing power, and the other is polarizability. Polarizability. Polarizing power is the ability of cation. Polarizing power is the ability of cation to distort the electron cloud of an ion so that it's no more spherical. So that the anion electron cloud is no more spherical. Polarizability is the ability of an ion. Polarizability is from the reference of an ion. So it's the ability of an ion to undergo distortion, by the effect of cation, So polarizability is of the anion and polarizing power is from the cation. Now, we have already talked about why magnesium ions were better at polarizing power than strontium. So we should write that down, that smaller and highly charged cations get more polarizing power. So if their charge density is more, small size and big charge, then they have more polarizing power. But when we talk about the anions, it's the reverse. So large and small charged, large sized and small charged anions have easy polarizability, or you can say more polarizability. So we can use this idea of polarizing power and polarizability to establish a very important concept. Let me show you that concept. And that concept is related to covalent character. It is related to covalent character in ionic compounds. Covalent character in ionic compounds. Let me give you an example. Let's suppose we have got let's take a very simple example, that same magnesium, and let's suppose we have the same sulfide. So magnesium was a small cation, sulfide is a big anion. And the other scenario we have is, let's suppose strontium oxide. So strontium is a big cation and oxide is a very small anion. So magnesium and sulfide, strontium and oxide. Magnesium is small in size, sulfide is large in size. Small cation means strong polarizing power, right? Strong polarizing power. And the large anion means easy polarizability, easily polarizable. So what happens is that magnesium ions get easily successful in polarizing the sulfide, so the electron cloud is distorted and it looks like this. It's not spherical anymore. Let me draw it more accurately. It looks like this. So this results in a kind of covalent character. It results in a kind of covalent character in magnesium sulfide because the electron cloud is distorted. But when we talk about strontium oxide was strontium ion which were large and oxide which was a small. Large cations have very weak polarizing power. So strontium is not good. Very weak polarizing power, and small anions are not polarizable. They can't be polarized. They are not polarizable. So it remains the same way it is. It remains exactly the same way. Let me just copy and paste it. It remains the same way. As a result, you can say no covalent character. Here you have no covalent character. When a compound has covalent character, what happens is that it can be easily thermally decomposed, and ionic compounds with no covalent character can't be. So let me write that down because it's a new concept we will talk about soon. Covalent character results in less stability, and no covalent character means more stability. So we are pausing the video here. First, let's revise everything so far. In today's video, we introduced the concept of ion polarization. We said that when it's an ionic compound, the cationic nucleus, the nucleus of the cation, pulls the electron cloud of the anion. Small cations can pull it better, large cations can't pull it better. Small cations pull the electron cloud so strongly that the anion electron cloud goes through distortion and it's not spherical anymore. Large cations can't pull the electron cloud, so the electron cloud is still the same way. It is still spherical without distortion. Polarizing power is the power of the cation to distort the electron cloud. Polarizability is the capacity of the anion to go for distortion. Small cations are good at polarizing power, and reverse is true, so large anions can be polarized easily. When the polarization of the ion happens and the electron cloud is distorted, a covalent character is created. And when the polarizing doesn't happen, so no covalent character is created. In the next video, we'll talk about this concept related to the group 2 compounds. Stay tuned. Thanks.